This is a visual report on the construction of ASMO and the first series of test runs performed on the proving ground of the Dutch Ministry of Transport. For the experimental validation of the complex mathematical model for the dynamics of a motorcycle, an automatically stabilized motorcycle was developed. ASMO is a motorcycle equipped with a rider robot, which stabilizes the machine and takes action to steer by interpreting radio-transmitted signals. The rider robot consists of the following components: the subframe to protect and to attach the components, pneumatic cylinders to control the brake, gearbox and clutch, a nitrogen supply tank with control valves, fuel tanks, a throttle servo, steering mechanism, a trailing arm sensor mechanism for measuring roll angle and roll rate, a velocity transducer, and a radio transmitter, relay box, recorder, and electronic control box. In more detail, the 12-channel transmitter, the steering motor, which introduces a torque up to 28 Newton-meter acting on the handlebar, the subframe and wheel-equipped outriggers. After unloading ASMO, it is prepared for the test runs.
Okay.
The outriggers are assembled on the subframe, providing stability at low speeds and in emergency situations.
Yeah.
The empty nitrogen supply tank is replaced by a full one. The fuel tanks are refilled a cassette tape is inserted and the antenna is mounted onto the electronic control box. As pursuit vehicle, a van is used. The portable radio control unit is connected with the antenna on top of the van. After starting the engine, ASMO is ready for a test run. While the outriggers are down, steering of ASMO takes place by introducing a steer angle through a radio signal. At a speed of approximately 50 kilometers an hour, the outriggers will be lifted. The stabilization circuit is then activated, and ASMO is running on its own, completely stable. The inputs for the electronic stabilizer are the roll angle, the roll rate, the steer angle rate, and the forward speed. The steer torque serves as the output of the stabilizer. The trailing arm sensors for measuring the roll angle sometimes jump up from the ground. But this has no effect on the measurement, as the roll angle signal is updated only when both sensors are in contact with the ground. The motorcycle was found to be stable above a relatively low speed. The stabilizer gain factors were experimentally optimized in a sequence of test runs. At slowly decreasing speed, by disengaging the clutch, the lowest velocity at which the vehicle remained stable was established. Because the trailing arm sensors are sensitive to wear and damage, an alternative method of measuring the roll angle was also used. An accelerometer mounted laterally measured the lateral component of gravitational acceleration. This can be interpreted as an indication of the roll angle. And with this device, successful runs were obtained down to minimum stable speeds of 40 kilometers per hour. The maximum test speed was 85 kilometers an hour, as this was the highest speed which could be reached by the van. Stabilizer gain optimization tests are being continued to achieve a stable system in a speed range from 10 kilometers an hour up to the maximum speed of the motorcycle. For the validation measurements, external disturbances such as a steer pulse will be imposed on ASMO. The rider robot replaces the human rider in order to achieve an objective and reproducible evaluation of the dynamic characteristics